Okay, let's start with this recurrence relation where we have a problem of size n, and that problem of size n is again divided into two sub-problems of size n by 2. So a problem of size n is divided into two sub-problems of size n by 2, and the local time required to divide a n size problem into two n by 2 size problem is n. So now this term is not constant, we have n here. So let's again do the same procedure what we followed. So our aim is to now reduce the t term from the right hand side. So that's why let's replace n upon n by n by 2. So what we will be getting? We are getting t of n, which is equal to 2 times t of n upon 4, and this n is replaced by n by 2, so this is n by 2. So this is step 1. Then again replace n by 2. So this is t of n by 2. Okay. So now this t of n by 2, if you replace n by 2, it will become t of n upon 4, which is equal to 2 times t of n upon 8 plus this n by 2 is replaced by n by 2 is n upon 4, right? So now if I replace n by 2 again, I will be getting t of n upon 8, which is equal to 2 times t of n upon 16 plus n upon 8. So same way the process continues. Now let's start putting our values whatever we have obtained here. So t of n, like again we'll just write t of 1 equal to some constant c. So now this t of n by 2 has to reduce to t of 1. So now let's go on replacing the values which we have computed here into this t of n. So our t of n will become 2 times, what is t of n by 2 now? 2 times t of n upon 4 plus n upon 2 and plus n, right? So now this will become 4 times t of n upon 4 plus 2 into n by 2 is n plus n, which is equal to 4 times t of n upon 4 plus 2n. This is t of n. Now again replace t of n by 4 by the formula which we have obtained. So see, this is the first step of our recursion, that the problem of size n was replaced to n by 2. Now the problem of size n by 2 have been replaced to 4 sub problems of size n by 4, and the amount of time required to do that is 2n. So similar way we will get next equation as 4 times, like t of n by 4 is 2 times t of n upon 8 plus n upon 4, and we had 2n here. So you can see that now it is 8 times t of n upon 8, and 4 into n by 4 is n, and n plus 2n is 3n. So we got here t of n as 8 t of n by 8 to 8 t of n by 8 plus 3n. Now if I replace t of n by 8 again with the formula which we have, which is equal to so what this indicates, again a problem of size n is divided into 8 sub problems of size n by 8, and time required to do that is 3n. So same way now 8 into bracket 2 times t of n upon 16 plus n upon 8 plus 3n, which is equal to, what we will be getting, 8 into 2 is 16 t of n upon 16 plus n plus 3n, which is equal to 16 t of n upon 16 plus 4n. Now if you observe, now what is our aim? We have to generalize this equation in terms of some value k. So now I will again write this generalized version as, if I go at kth stage, because this is fourth stage and I am getting 2 to the power 4, so I can write it as a 2 to the power k t of n upon 2 to the power k plus k into n. Can I say that? Now see what we obtained, t of n is 2 to the power k t of n upon 2 to the power k plus kn. So now put k equal to 1, what we will be getting? 2 times t of n by 2 plus n. That is what our initial recurrence relation. If I put k equal to 2, 4 times t of n by 4 plus 2n, that is also we obtained here. Then if I put k equal to 3, it is 8 times t of n by 8 upon 3n, that also we got here. Now put n equal to 4, that is 16 t of n by 16 plus 4n. So this is right. Now what is our aim? Now our aim has to bring this term, whatever the term which we have here, n upon 2k should be equal to 1. So now when I write n upon 2 to the power k is equal to 1, I will be getting as n equal to 2 to the power k. And again what k, because we need k again here in this case, so that's why k equal to log of n to the base 2. So this value we got. So now replace this value in this above equations. So now I will be getting t of n equal to 2 to the power k is again n into t of 1 plus k is log of n into n. So I will be getting c into n plus n into log of n. So which is bigger, n or n log n? So n log n is higher and n is smaller. So this t of n I can write like this, n log n plus cn. So now I could just say that the complexity of t of n, which is equal to 2 times t of n upon 2 plus n, is, if I choose the highest degree from this equation, so I have the equation t of n equal to n log n plus cn, and the highest degree here is this one, that is n log n. So this will give me big O of n log n. So the big O, and what was our capital omega or omega notation, which is giving a lower bound. So if you look at this equation, for any value of n, after some point, like after some value of n, if you just put n and if you just look into this equation, this cn will be forming a lower bound, because the value of n log n will be always lesser than cn. So if you just look at the graph, so this is the graph of n, but for n log n graph, maybe initially it is 0 and then it may go increasing like this. So you can see that after some point this n has like this whatever is there, the n log n will be higher, always higher than n, and that is why we can also say that the complexity of this recurrence relation is omega of n. But we widely follow the upper bound notation, that is why we will go with this one. And if you remember the merge sort algorithm in your data structures, the merge sort algorithm have a complexity of big O of n log n, and this log n base is 2, and even if you can say this is also a fine, but widely followed notation is big O, so we will go with big O of n log n to the base 2.